Today we are very pleased to invite Professor Lin Chen-Hong to give us a talk. Professor Lin received a PhD degree from the Graduate Institute of Electronic Engineering from National Taiwan University. In August 2010, he joined the faculty of the Department of Electrical Engineering in Yuanshi University. Now he's a full professor. His research interests include the design of real-time signal processing for communication system, memory system, digital signal processing system, artificial intelligence for medicine, and so on. His talk today is titled Reconfigurable Forward Operation Decoders for Consumer Communication System. Okay, let's give applause to welcome Professor Lee. Welcome.
Okay, good morning, everyone. I'm Chen Hong Lin, and I currently also serve as chairperson in Program A, Department Electrical Engineering, YZU Taiwan, and also serve as the vice chair in Technical Committee, IEEE Consumer Technical Society, IEEE CTSOC. And as mentioned by Professor Wang, my research area interest, my main focus will be U.S. assistance for related to full error correction codes and artificial intelligence in medical image processing. So several years ago, I just gave a talk here to talk about the artificial intelligence in medical image processing. Right now, I would like to give another topics about the whole error correction code. Okay. So the title of this speech is the reconfigurable. You can call whole error correction code decoder or channel decoder designs for consumer communications. Then the subtitle is from static hardware to flexible performance, because we just give the reconfigurability to the decoder design. So here's just the outline. First, I would like to give some introduction and background of this topic about the motivation and the consumer communication trend. Most of important of all is today's topic, channel coding overview. I would like to give some importance of the important role of the channel coding in the consumer communications. Then, because the involving of the consumer communications, then I would like to describe the channel challenges and the goals of these designs. Then, the second part introduces three reconfigured decoder designs for POLA, Chevron, and the LDBC low density parity check codes, followed by the conclusions and insights for future systems. So before giving the main concept, I would like to describe the simplified communication chain. I think most of you just have already known about this, and some of you have been familiar with this area. Okay, so as you can see that here shows the original image. Then we just transmit this image to the communication systems, such followed by the modulation channel and the noise and the demodulations. And if we do not have the channel codes or channel encoding or decoding, then we will get the noise image like this. However, if this original image is encoded by the channel code, then after decoding, we can get the clear image. However, you can see that there is still some noise because the channel quality is so is not good. It's very bad to this system. Okay. But you can see that what is the importance of the channel codes. So most of you could not know that there is a channel code in the communication system. Even there would be a channel decoder in the communication systems. Channel decoder can be regarded as the hidden hero for the consumer connectivities. So every message we send can be reconstructed by the channel decoder. Then I would like to describe the consumer communication trend. As you can see that here shows the first generation consumer communication systems. We only send the text or not text. We just do the voice communications via the mobile phone. And as the evaluations of the consumer communications, we have more requirements or demands. For example, from 2G to 6G, we require high data rate. Even now, we need gigabit level user throughput demands, and currently we also require ultra low latency to perform the VR, AR for autonomous applications. Then, because we would like to put these communication systems into the mobile devices, so energy efficiency becomes very important. So energy efficiency is very essential for mobile or Internet of Things devices. And we also need massive connectivity. For example, billions of the connected nodes in IoT area. So based on the above demands or requirements, these factors shows that we require scalable and reconfigurable architectures shown in this figure. Okay, so based on the previous slide, we know that the consumers have increasing need demands for the communications. So we, for example, in 2G, we just transmit the voice. Then in 3G, we need to transmit data. Then that's not good enough for the 4G. Then we think multimedia should be transmitted using the communications. And then need connectivities for social media, then we require the 4G, 5G, 5G communications. Then when it comes to 6G, AI becomes more important. Though then we will do the intelligence applications. Then we require high speed, low latency transmission, and the robust transmission. Okay, so as the evolution shown above, has our hardware keep up with the evolution of the consumer communications? Okay, how to keep up? So let us go back to the channel code. So okay, as mentioned before, we have shown the communication chain here. Channel coding plays an important role in this communication chain. Okay. Channel codes are very essential for error correction and reliability, as shown before. If we do not have the channel code, the data will deeply disturbed, okay, or noised. So if we apply the channel code into the communication system, then we can get a high quality image or data. So channel codes plays an important role in the consumer communication systems. However, there are several types of the channel codes or for error correction code. For example, conversion code and the turbo code are applied to 3G or 4G communication system or home plug systems. And right now, CC and TC code was abandoned because by the communication systems because the features of their low latency. Okay, and there are other type of channel codes. For example, low density purity check code or polar code. These two codes provide high throughput because of the variable design and interpretation strategy. So 5G just adopt these two channel codes, and G.HN also adopt this LDBC code, Polar code has another feature, good feature. This feature is the flexible coding length. We can have the distinct length for the transmission. Okay. Okay. So I think most of you has some fundamental, some background of the consumer communications and channel codes. So I would like to describe the challenges in this design. The challenges in multiple standards and distinct algorithms. So features that diverse code structures, for example, CC, TC, LDBC, polar code, they are quite different in their code structures. So how to support different code type, code length, and the code rate becomes very important and challengeable. Okay. And the other topics, if we want to design the decoder in hardware, using the hardware, for example, ASIC design or FPGA design or other types of design. Hardware reusable. Hardware reuse is another main topic for this for the design of the channel decoding. It is very difficult to share functional units across decoding algorithm. We have to analyze the decoding algorithm in detail. Then we have to find out which part can be shared and which part cannot be shared. Then we have to require the design efficiency for the channel coding, decoding, channel coding. And the other one is power constraint, because we want to implement such as consumer electrical consumer decoding architectures into the IoT or mobile devices. So the power or energy become very important. So we need to achieve the power efficient or energy efficient design to have the good devices implemented into IoT or mobile application or devices. So power constraints become very important. Limited energy budget for because we need to consider limited energy budget for the mobile edge devices. And scalability is another issue because scalability can be regarded as a way to get the high throughput design. Okay, high throughput design. For example, if we want to get 100 gigabit per second, the data rate about 100 megabit per second, then we can put, for example, if one decoding core or decoding kernel, kernel can be regarded as the basic or kernel or core. Decoding kernel or decoding core can be considered can be regarded as the fundamental building block of the decoder, small block decoder. If we assume that one kernel can achieve a gigabit per second, then if we require 100 gigabit per second, ideally we can put a parallel 100 decoding kernels or cores into the decoder. Okay, so if we want to get 10 gigabit per second transmission, ideally we can put 10 decoding kernels or cores into the decoder. That means the scalability. Okay, scalability. So if we have less throughput, we use less hardware. Okay, if we require high throughput, we need high hardware. Okay, so the scalability becomes very important to have the balance between the hardware cost and throughput data rate. Okay. This means that hardware must scale across multiple performance targets. Okay. So another one is interoperability. Okay. Because there are so many standards in the consumer communication systems, so if we want to achieve the coexistence of the Wi-Fi, 5G, or power line computer using the one devices, okay, this becomes very tough to do the hardware sharing or reconfigurability. So I think most of them are big challenges to do the reconfigurable design for the consumer applications. So we need we have a need for the unified or reconfigurable decoding frameworks. This is the solutions. Okay, so as mentioned before, the reconfigurable architectures can deal with the above challenges. So I would like to mention this part in detail. As you can see that there's illustration about for the different implementations. Usually we have an algorithm. We can implement the algorithm using the CPU. Okay. However, using the CPU achieve high power and high flexibility. Okay, high flexibility means that we can just modify some parameters using the code. For example, we just using the if we just using we can use some parameters to deal with the distinct algorithms, okay, or distinct length or information bit. Okay, it's quite easy to deal with this using the CPU. Another way is to implement the architecture by FPGA, because FPGA can be implemented several times. Okay. However, if we want to not erase, program the hardware into the FPGA, we still need another device to do so. We still need another instrument, I think, not device, instrument to do so, to reprogram the FPGA. Okay. However, but if the FPGA has been programmed, it can it can perform the algorithm efficiently, but not in high performance, high efficiency. Okay, and another way is ASIC, application specified integrated circuit. Okay, you can see that it is designed for dedicated hardware. ASIC, as you can, I would like to mention that ASIC means the IC design. Okay, for certain applications, IC design. So if we design the certain architecture and implement the architecture in an ASIC, then the decoder or then this architecture is fixed. Okay, we cannot reprogram it. Okay, because it is a dedicated hardware. Okay, so if we do the reconfigurable architecture, then we can have the performance between ASIC and the FPGA using the reconfigurable architecture. Okay, so reconfigurable architecture can achieve median performance efficiency and median, I think, median, high median flexibility or power. Okay. So static ASIC decoder cannot adapt it. As mentioned before, static ASIC decoders cannot adapt it to new standards or new algorithms. However, FPGA implementations offer flexibility but limited efficiency. If we want to implement another algorithm or architecture, we must use another instrument to reprogram FPGA. So our goal is that we have to design ASIC level hardware with FPGA like flexibility. So reconfigured architecture can achieve this goal. Because reconfigured architecture provides high flexibility, high performance, and low design efforts. The key strategy is modular and parameterized decoder cores. Okay, and and the important target is shared hardware resource. We have to analyze the algorithm, and we have to find out which part can be shared and which part cannot be shared. Okay, and we have to increase the shared hardware parts. Okay, and we must achieve dynamic configuration of the decoding parameters. Decoding parameters. Okay, so here shows the end design example, which was my PhD research. Research. It's I think it's about 20 years ago. 20 years ago. So as you can see that when we want to discuss the consumer communication systems. So 20 years ago, there are two types, two standards. One standard is 3GPP, and this one is proposed by European authority. Okay, and the other one is the WiMAX. And the WiMAX is US-based standard, and one of the big company to support this standard is Intel. So when that year, past decades, okay, these two standards were regarded as the future of the 4G communication systems, and there are okay. Let us see the maximum data rate shown here. Okay, inside 3GPP, the highest standard that year is LTE long-term evolution. Okay, and the throughput is about 100 megabit per second. And in WiMAX, WiMAX 2 still requires 100 megabit per second. Okay, and the decoding fee, the channel coding fee for the 3GPP, the single binary turbo code is adopted, and in WiMAX, double binary turbo code was adopted. Although they are holders turbo code, but because one is single binary, the other is double binary, the decoding algorithm are somewhat different. So we just want in my PhD study, I just wanted to build up a hardware shared architecture to deal with both standards. Then I just designed architecture and implemented it to have the recompatibility to get the both communication systems. So it means that we can use only one chip to get the transmission, to achieve the transmissions in LTE systems or WiMAX systems. Okay, then we can achieve the transmission efficiency among these two standards using the one hardware. Okay, so I would like to show the importance of the reconfigurability. So this is my selected journals related to reconfigurability or reconfigure channel decoders. So in this speech, I would like to describe three parts, three research about the reconfigurable channel decoders. And so first, I would like to describe the recent publications. Okay, hybrid BP-based SSCF polar decoders for the 5G beyond consumer communications. Okay, so let us go to the second part of this speech. Three publications related to the reconfigurable channel decoder. The first one is hybrid polar decoder for 5G and beyond consumer communications. Okay. So 5G and beyond communications require high throughput and low latency. Okay, high throughput and low latency. Okay. So polar codes are adopted by 3GP released 15 for EMBB scenario. Then there are two types. There are two decoding algorithms for the polar decoding. One is the blip propagation decoding algorithm, BP algorithm, and its features are high speed but weak error correction ability compared to successive cancellation decoding algorithm. Successive cancellation decoding algorithm is another type of decoding algorithm for the polar decoding. Okay, SD decoding has stronger correction ability, but the latency is too high compared to the BP algorithm. Okay, so one is high speed but weak correction. One is stronger correction but high latency. Okay, so our goal is why not to get two of them, two advantages of them. Okay, so our goal is to combine BP and SC advantages for consumer for 5G communication systems. Okay, so based on this figure, then we want to implement both algorithms into one architecture. Then we can get reconfigurability among these two algorithms. Okay, so as mentioned before, why not to build them together? Build the two decoding algorithms together. So hybrid decoding algorithm was proposed to retrieve features the hybrid decoding decoders. We want to retrieve advantages of BP and best simplified SC flip. This is an enhanced version of the SC algorithm. Best simplified SC flip algorithm, best SSCF. Okay, and this is the algorithm label. In algorithm label, we try to implement it and implement them into one data flow. And we want to, in the second step, we want to build these two algorithms into one architecture. And we just implemented this architecture, and we can get a triple mode decoder. And in this triple mode decoder, we can achieve BP decoding only, fast SSCF only, and hybrid decoding. So we call this triple mode decoder because there are three modes as we talked before. Okay, so a triple mode decoder with a hybrid decoder core supports the BP, fast SSCF, and propose the hybrid decoding. So on the other hand, we use the hardware sharing architecture to reduce area consumption. Okay, I think this is the two technical parts. I like to mention it in a quick way. Here shows the encoding information about the product code. Here shows the encoding structure of the product code. And each node is the clock code power shown here. So if we regard this part one, we have the function shown here. So in this decoding structure, we can have the information shown here, and the code shown here, information shown here, and product code has the information about the channel quality, after some analysis. Okay. So after some analysis, we can have some positions. Some positions have less channel quality. Okay. Then we can put 0 here. 0 here. Non-function. 0 here. We call it frozen bit. Frozen bit here. It cannot be used for the information now. And after encoding, we can have the code word. We can have the code word here. So if you are familiar with the communication, you must remember that information information bits are less than code word bits. Okay. This is we can guess the parity. But with the parity bits, then we can use the parity bit to recover the information bits. This is how channel decoding works. Okay. So for example, I would like to say that I'll make that bigger as an example to that some people, some students who do not familiar with the this area. Okay. For example, if we have 4 bits here, okay, and these 4 bits are not good enough for the transmission, we call it frozen bits. 4 bits here. Then we just assume that 4 bits are information bits. After encoding, then we can get code word bits. Then code word bits are 8, shown in this figure. Okay, so 4 bits in, 4 information bits in, 8 bits out, 8 bits out. Then we can get the code rate. The code rate is 4 over 8. 0.5. The code rate is 0.5. Okay, so you can see that only 4 information is transmitted. I'm not sorry. Only 4 bit information is encoded. Okay, but 8 bit code word are transmitted. Okay, so you can see that there are 4 bit parity. for bipparity. So the fourth parity is used to protect the information. Okay, this is the main idea of the channel code. Channel code. Okay, let us go back to the this encoding structure. Okay, if we have the encoding structure, how decoding works, then I would like to describe the BB decoding, bit propagation decoding algorithm. I would like to skip this mathematical part, okay, because most students or most people do not like the mathematical expressions, okay. So I'll try to use this part to describe the BB decoding. Okay, sorry, forget that to mention that if we want to get high quality transmission, okay, usually we adopted probabilistic decoding algorithm. We decode we decode the information or convert using the probability, using the concept of probability. Okay, so in decoding, we call probability, especially log domain of probability. Okay, and we just processing them by using some mathematical strategy. We call it log library or hood ratio, or LLR, so LLR represents the probability-based information for mathematics. Then we can do the mathematical calculations using the probability-based information. Okay, and we call this type as the soft decoding, soft value decoding. Contrast to the soft decoding, hard decoding means binary information decoded with 0 and 1. 0 and 1. We call this type as the hard decoding. If we want to get high performance, high correction performance, we usually use the soft decoding. And the soft decoding is more complicated compared to the binary decoding. Because if we want to represent soft decoding, we have to use floating point digital system, digital number representation, or tooth complement number systems. So you can get that soft decoding soft decoding has more complicated calculations compared to the binary decoding, hard decoding. Okay, and the BP decoding is belongs to the soft decoding. Okay, let us go back to this decoding structure. As you can see that the decoding structure for the BP is very similar to the encoding structure. Okay, so in BP decoding, we just use the right probability information and the left probability information. And we have the two probabilities. Then we just transmit left information, left, you can regard this as a left probability. We just transmit, we just do the calculation from right to the left. Another way, we have the right information. We just calculate right information from the left to the right. Then we can get two probability information. Okay, Then we just do the iteration. We just do the iterative calculation to increase the probability. Then, after several iterations, we can guess reliable probabilities. Then we can guess the exact decoded half bit or binary bit based on these probability informations. Okay? Okay. So this is how soft decoding works, and this is how BP decoding works. Okay. Many calculations using probabilities. Okay? Or soft decodings. Okay. I think these descriptions are good enough. Okay. I do not want to give more details. Okay. So as you can see that there are two information. There are two parameters from left to the right, and from right to the left, and left to the right. Okay, shown here. Here, and the fundamentals of the f function is the maxima, slack, compare stack. You can regard it as a multiplier calculation. This calculation just find the maximum value. Just try to find the maximum value among the two information parameters. Okay. So here shows the right calculation and the left calculation. Okay. So as you can see, that the calculation is very complicated. Okay. So after several iterations, we can guess the hard information. Okay. So limitations of the BP decoding is requires high pluralism, but low latency, but high power and area. Okay, and another type of the BP is the BPF. And the BPF can improve error correction, but increase complexity. Okay, so because BP is quite complex, so in our design we do not use BP for the BP. We just use the simple BP. And BP lacks robustness at low SNR and the channel variations. So we have we need a hybrid approach of preserving BP speed and improve accuracy. So here shows another type of the BP decoding. For the polar decoding, successive cancellation decoding. Okay. Successive cancellation decoding is the serial decoding. Now period decoding shown here. In BP decoding, we can have calculations in one stage, Then we, for example, in this figure, we can finish the left to right in three stages. Okay. So in three stages, we can finish one iterations for left to right calculation. However, in SD decoding is based on node. If one node is calculated, then we go to the other node. Okay, so we regard this as the serial decoding. Now, however, because of the serial decoding, okay, it suffers from low latency. Because it needs more time, more cycles to do the calculations. You have to remember that. But SD decoding can get high error correction ability. Okay, so there are several advanced SC decoding I would like to mention in this slide. For example, SD list. SD list can maintain multiple decoding paths to explore alternative bit decision. It achieves near ML performance at the cost of the high capacity and the memory usage. Okay, you have to remember that high memory usage. Okay, and it also requires a large sorter to sort, to do the sorting. Okay, so the large sorter makes SCL not efficient to do the polar decoding. Okay. Another one is SC-based decoding. We just flip the unreliable bit and do the SC decoding again. Okay, after calculation. So you can see that there is an iteration in the SD decoding. We do the flip. If what I would like to give it a little bit detail. So once we perform the SC, okay, then we do the some parity check or CRC check. Then this SC is not reliable. Okay, then we flip one bit to do the calculation again. Okay, then we can increase the reliability. Okay, based on flipping and recalculation. This is the concept of SCF. Okay, and there are another type of fast simplified SCF, SSCF. I would like to describe it a little bit detail. How to simplify? As mentioned before, there are frozen bits in polar decoding. Encoding frozen bit. Frozen bit is useless. Because it is zero. So we can in SCF calculation, simplified calculation, we can use this concept into the decoding. Okay, just simplify the calculation for the frozen bit. Okay, so SCF can achieve excellent error correction performance, but the serial nature limits serial decoding limits the throughput. Okay, so here shows the simulations. Okay, simulation Fresnel rate. Fresnel rate as shown here. You can regard as the error rate per cohort. Error rate per cohort. And the x denotes the channel quality. Channel quality. So you can see that the SD decoding shown here. SD decoding. Here shows the performance Fresnel rate of the SD decoding. So you can see that how to evaluate the algorithm based on this figure. Okay. If the algorithm fixed in this part, we can regard as a good algorithm. Okay. So SD is higher than others. Okay. So how about others? As you can see that BP is not good enough scale because their performance is higher than others. So how about SCF or fast SSCF? As you can see that the performance is quite good. Okay, it means that we can have the low frame error rate at low channel quality. Low channel quality. So how about the latency? This part shows the latency. As you can see that the BP achieve the because we applied early termination to do to cease the iteration. So as you can see that the high channel quality can get low latency. Okay. And as you can see that the SC based SC family decoding achieve high decoding latency compared to the BP. Compared to the BP. Okay. So these two figures demonstrate that BP achieves low decoding latency, and the SCF achieves high correction ability. So how about to achieve two advantages? This is really our goal, our main goal. So we proposed a two-stage adaptive decoding. Okay, we in brief we do BP first. Okay, because BP has high throughput, low latency. Okay, if this code cannot be decoded by BP, then we transmit this code to SCF. That's how it works in brief. Okay. Okay. After our analysis, we just analyzed. We can get that using the early termination in high quality, in high channel quality, most code can be decoded by BP. Only few codes fails. So we just transmit it to the SCF. Okay. Using this concept, we can reduce around 79% latency compared to the BP. Okay, compared to the BP. Okay, so we proposed a hybrid decoding algorithm shown here. So I'd like to describe the FER directory. As you can see that FER is shown here of the proposed hybrid BP and the best SSCF. As you can see that, and others are higher than our proposed hybrid decoding algorithm. And the other one is average decoding latency. As you can see that the proposed hybrid decoding algorithm achieve the latency similar to the BP. Okay, so based on this two-stage flow, okay, based on the hybrid decoding, then we can get the advantages of the BP high throughput, low latency, and high correction ability of the SCF. Okay. Okay. We just deal with the first algorithm part. Then we must propose the hardware shared architecture. Okay. Here shows the overall architecture. And this architecture is based on the BP algorithm. Okay, because as I mentioned before, BP is more complicated than SC. So this architecture is based on the BP. Then we try to find some hardware in BP to do the SC calculation, So let me go back to the further the previous slide. Here shows the calculation of the BP, main calculation of the SC, and here shows the calculation of the BP reference. It is similar. Sorry, they are similar. They are similar. So as you can see that in BP there are two decoding cores. Then we try to find one to implement SC into the decoding core. Okay, decoding core. So in this figure, a white block denotes the hardware share part. Okay, and the blue part denotes the BP only, and the pink part denotes the SSCF only. Okay, so unfortunately, there are still large parts cannot be shared, but we still get the hardware efficiency. Okay. So here's just the analysis. Okay. If we implement standalone BP decoder, yes, we just in this research we build up hybrid decoder, standalone BP decoder, and standalone fast SSCF decoder. Okay, and so we implement these three decoders using TSMC 40 nanometer CMOS process. Okay, then as you can see that hybrid decoder, here shows the total area of the hybrid decoder. The unit is micrometer square. Meter square. Okay, and this table shows that if we want to have a standalone BP and a standalone SFCF, okay, we must in previous way, in conventional way, we must have a single hardware of this part and a single hardware of this part without hardware sharing. If we do the hardware sharing, then we can have area shown here. Okay, so it means that we can have 7.70% area reduction in this research. Okay. Here's just the latency and the power. Okay, we analyzed the latency and the power in high. I think based on the previous observation, we regard this 2.5 dB as the low channel quality. Okay, and we regard this 4.0 dB as the high channel quality. Okay, so in low channel quality, okay, we can achieve in our hybrid mode, we can achieve 0.64 dB because several cohorts are decoded by BP algorithm. Okay, and in standalone SSCF, the latency is quite high, as shown here. Okay, in high channel quality, we still can get the same condition, same result. Hybrid can get high latency, low latency. Standalone SSCF achieve low latency. How about the throughput? BP can get high throughput, okay? But low frame error rate. If we apply our decoding algorithm or hybrid decoding, we can get a little bit higher than SC. The throughput can be higher than SC, but lower than BP. However, the frame error rate is similar to the not similar, less than SCF, okay, and higher than the correction ability is higher than BP. So in high channel quality, we still can get the same result. Okay, so here shows the decoder or chip comparison. We compare our work with others' work. Okay, others are standalone decoding algorithm. For example, these three publications, 3 studies belong to BP-based decoding algorithm. And these 4 studies belong to the SCF decoding algorithm. So as you can see that in our work we can achieve high throughput, shown here, the most high throughput in BP mode. In hybrid mode, we still can get comparable result compared with others, and we can get low latency compared with others. Low latency, as you can see that low latency because we just applied 4th algorithm into this architecture or decoding. Okay, so this table shows that we successfully get the good hardware, good reconfigurable design in 5G communication systems. Okay, and so I would like to mention this part before. Okay, according to the past slide, you can see that using the reconfigurable architecture, we can get high flexibility, low power, high energy efficiency. Okay, and we can get high throughput, low latency in this design. This is the benefit of the reconfigurable architecture. Okay. So in summary, we have the hybrid BP and that's the SSCF provides multiple trade-off between throughput, latency, and correction. We also do the reconfigurable mode. BP achieve low latency. Fast SSCF achieve high correction ability, and we do hybrid mode to achieve the balanced design. So achieve the first triple mode decoder, polar decoder for consume 3G beyond. Okay, I would like to skip this part because it's too many. In our lab we do a lot of research related to reconfigurable channel decoder, but time limitation. I cannot share them share most of them all with you. Okay, and this is very interesting topic I would like to mention. We also do the chip layout. These two slides shows that reconfigurable architecture can also reduce routing in chip if we do the analysis in detail. For example, this is another work. Okay, this is the direct routing method. As you can see that the routing is quite complicated. Okay, if we do the reconfigurable and reconfigurable design and do the design in detail, okay, and analyze it capacity, we can reduce the routing significantly. Okay. Okay, so let us go to the let us conclude this work. So complications keeps evolving. Okay, reconfigurable architecture enables adaptability among distinct algorithms or different standards. So hardware reuse enables area efficiency, as I mentioned before. Okay, so flexibility is not the opposite of efficiency. It is a fundamental part of the reconfigurable architecture. So reconfigurable architecture achieves high flexibility, high decoding performance, and low design efforts. Okay, so that's all my talk today. Thank you.
Okay. You use a two-step decoder. First, you apply BP. If start decode successfully, you will apply SC, right?
Yes.
I'm wondering, because you always first use BP and then SC, maybe I think it can depend on channel part.
Yes.
For example, if the quality is good, maybe you can apply SC.
Okay.
Because I think BP is good for the latency, right?
Yes.
So if the channel is good, maybe we can use SC.
SC. But SC is.
Depend on the channel quality.
Yes. But
with probability.
Yes. We can do so, but if we have to do so, we need a strong channel estimator.
Yeah.
Yeah.
You estimate the channel quality.
Yes. We have to know the channel quality for each cohort. Okay, and we have to take the channel quality for this cohort. You just mentioned a good question.
It's a very expensive cost.
Yes. But in many communication systems, a strong and real-time channel estimator is very tough. Yes, and it's very tough and expensive. It's not easy. Yes. But as you mentioned in this question, in our design, if we have a stronger channel estimator, okay, then our decoder has strong ability because there are 3 modes.
Yes.
Okay, then we can go this mode directly.
Okay. Thank you.
Thank you.
No question? Do you have any student in Professor Lai 那一位老师的 lab 做那个physical lab?
I know Lai Wei.
Okay.
Lai Wei do the similar research.
Yes.
About
Quality.
Yes. He also do the iterative MIMO.
Yes. Okay. Today we are very pleased to invite Professor Lin. He gives very impressive and valuable speech. Let's give a big hand to Professor Lin again. Okay. Thank you a lot.